a subtle wobbling in the light of B. It could be a sign of tugging from a planet's gravity. If a planet is there, it literally hugs its parent star, with an orbit that's even closer than Mercury is to our Sun. It's probably molten, with surface temperatures in excess of 1,000 degrees centigrade. Are there other planets far enough out for liquid water to flow? That prospect is the subject of intrigue in science and science fiction. Alpha Centauri is the fictional location of Polyphemus, a giant gas planet, and its moon Pandora from the movie Avatar. The year is 2154. Earth has been ruined by environmental catastrophe. Greedy prospectors board the hybrid fusion antimatter spaceship, Venture Star. They descend on an innocent hunter-gatherer people called the Na'vi. Could such a place exist this close to home? One problem with Alpha Centauri is that the orbits of A and B bring the stars as close as Saturn is to our Sun. This means that planets further out could have been pulled away and flung out into space. For this reason, Alpha Centauri was not a high priority for planet hunters. That is, until similar examples turned up, such as Kepler-16. 16b is a planet that orbits two stars, which in turn orbit each other. Or Gliese 667, a triple star system 22 light-years from Earth. 667c is a red dwarf, 1/3 the mass of our Sun, with 6 planets in its fold. 3 of them, small enough to be called super-Earths, orbit at a distance that could allow liquid water to flow on their surface. That opens the possibility that planets may have survived in the Alpha Centauri system. For now, that question is on hold. The orbits of Alpha Centauri A and B have brought them too close for astronomers to resolve the signal of a planet. When they move apart again, astronomers will have new tools at their disposal, including the James Webb Space Telescope, now set for launch in 2018. From a position 1,000,000 miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. Astronomers will use this telescope with its infrared light detectors to discern the chemical composition of planetary atmospheres. Here are Alpha Centauri A and B, as seen by the Cassini spacecraft just above the rings of Saturn. Assuming it's worth the trip, you'd have to travel a distance 30,000 times the orbit of Saturn to reach them. Put another way, if Earth to Saturn is a meter, then Earth to Alpha Centauri is New York to Chicago. To put the journey into perspective, consider Voyager 2, now on its way out into the galaxy. After a series of gravitational assists from Jupiter and Saturn, the spacecraft is traveling at about 62,000 kilometers per hour. If it were headed in the right direction, it would need another 73,000 years to reach Alpha Centauri. The dream of traveling to other solar systems was forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit and eventually permanent space colonies. Someday, he predicted, we'll evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem with chemical rockets is that they are just not very efficient.
3 engines up and ready. 3, 2, 1.
To reach the speed needed to escape Earth's gravity, 25,000 kilometers per hour, the space shuttle carried 15 times its weight in fuel. A NASA study showed that to send a shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms worth. That's more than the entire visible universe. There are several promising advanced propulsion concepts on the drawing board, including fuel-efficient plasma engines, which accelerate a spacecraft gradually to high speeds. It won't get us to Alpha Centauri in anything close to a human lifespan. To go that far and that fast, a pre-Apollo project called Orion called for a series of controlled nuclear explosions to propel a spacecraft to high speeds. The project died amid concerns about the impact of nuclear explosions on the environment. Back in the 1970s, a group of scientists unveiled designs for Daedalus. This giant fusion-powered craft would have had to carry 50,000 pounds of fuel. The plan was to accelerate to 12% the speed of light and reach a nearby star in 50 years. Other plans have included ramjets with vast magnetic fields that scoop up a fuel supply of hydrogen ions, or solar sails powered by the solar wind and by lasers stationed along the way. Then there's the rocket of choice in science fiction, powered by the most potent fuel in nature, antimatter. In James Cameron's Avatar, a fusion antimatter hybrid engine powers a 1,500-meter-long spaceship. It makes the journey to Alpha Centauri in just 6 years. Antimatter consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Only trace amounts can be found in the universe today. For example, in the high-energy environments of black holes. It's so powerful that a mere 10,000th of a gram is about all it would take to send a spacecraft to Jupiter. Current designs for an antimatter drive use magnetic fields to isolate and channel the fuel. The idea is to merge a stream of protons with a stream of its antimatter opposite, antiprotons. A magnetic field pinches or compresses the combined streams into a narrow beam. Annihilation then produces an ultra-high energy laser that shoots out the back of the craft. That causes a recoil effect that pushes on the magnetic field produced by the beam and propels the craft forward. Antimatter can be produced on Earth in giant physics labs like the Large Hadron Collider. Here, scientists accelerate atoms to nearly the speed of light and blast them together to release their fundamental constituents. The yield is so small that the cost of producing just a gram's worth of antimatter would be upwards of $100 trillion. And the stuff is so volatile that storing more than a few atoms at a time remains a significant challenge. If specialized facilities were built, the cost could drop by one estimate to as low as $10 billion per gram. One idea would be to station an antimatter factory in space, powered by the 1 billion watts per kilometer delivered by the sun. Another is to harvest antimatter already produced in space. The idea is that cosmic rays, interacting with interstellar particles, send about a kilogram of antimatter flying into the solar system every second. Some of it has been shown to circulate in radiation belts that surround the Earth. Theoretically, it could be captured by a large magnetic scoop that sits in a high orbit above the planet. Short of traveling to another solar system, there may be good reasons to develop antimatter propulsion. An interim mission would speed beyond the orbit of Pluto, sending back close-up images of objects in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample interstellar particles or deploy an interstellar telescope. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to accelerate to around 10% the speed of light, over 100 million kilometers per hour. High velocity has its perils. At such speeds, even dust has enough mass to destroy the craft. A magnetic shield would be needed to clear the way. If it could be done, there may be other destinations to consider. At least 22 stars within 12 light years of Earth. Any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peak, is a vital part of human nature. But explorers of old set off not just because it was there. At times it was greed, hunger, fear, and despair that propelled them from their homelands and allowed them to endure their long journeys. What imperatives will send future generations into space? To the physicist Stephen Hawking, it's a question of survival. "I don't think the human race," he said, "will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet." We can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But an early context for the mission may be emerging now. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing number of transistors that can be placed inexpensively on a computer microchip has become a metaphor for the advance of technology. Some observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. In addition, despite the daily drumbeat of violence and war, we are actually living in one of the most peaceful eras in human history. Over the centuries, the number of people killed in battle has steadily dropped as civilizations evolved. With 2 world wars, the 20th century was pretty bad, but the 19th was even worse. In terms of deaths per 100,000, from war, genocide, murder, and other factors, the world is relatively calm. On the other hand, major periods of scarcity and suffering may loom. The last century saw the world's population grow from less than 2 billion to nearly 7 billion today. It may reach 9 to 10 billion by the year 2040. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. Simple, clean water in some regions is already extremely scarce. Now throw in environmental impacts like rising sea levels, or the spread of deserts linked to a gradually warming climate. No matter how you look at it, our world is changing in ways that will impact the way we live and relate to each other. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the effects of war, natural catastrophes, or political upheavals? The technology needed to launch a first interstellar mission is certainly decades away. The actual journey could take centuries. The mission will likely be designed to relay basic information on a world whose light we have studied intensively from afar. Back home, it will no doubt spur reflection on who and what we have become as a people, as a planet. As our cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness, prosperity, and mere survival. When it arrives, we'll scan the data for evidence of a world like our own, one that may harbor life. Will we come to explore and expand our knowledge, or to begin a long journey out into the uncertain reaches of the galaxy?
The year is 2154. Our planet has been ruined by environmental catastrophe. In the movie Avatar, greedy prospectors from Earth descend on the world of an ancient hunter-gatherer people named the Na'vi. Their home is a lush moon far beyond our solar system named Pandora. Could such a place exist? And could our technology and our appetite for exploration one day send us hurtling out to reach it? In fact, the supposed site of this fictional solar system is one of our most likely real interstellar targets, until a better destination turns up. Pandora orbits a fictional gas planet called Polyphemus. Its home is a real place, Alpha Centauri, the brightest star in the southern constellation of Centaurus. At 4.37 light-years away, it's part of the closest star system to our Sun. Alpha Centauri is actually two stars, A and B, one slightly larger and more luminous than our own Sun, the other slightly smaller. The two stars orbit one another, swinging in as close as Saturn is to our Sun, then back out to the distance of Pluto. This means that any outer planets in this system, anything beyond, say, the orbit of Mars, would likely have been pulled away by the companion and flung out into space. For this reason, Alpha Centauri was not high on planet hunters' lists, until they began studying a star 45 light-years away, called Gamma Cephei. It has a small companion star that goes around it every 76 years. Now it seems it also has at least one planet. That world is about the size of Jupiter, and it has planet hunters excited. Perhaps 2/3 of all the stars in our galaxy are in so-called binary relationships. That means there could be many more planets in our galaxy than astronomers once assumed. At least 3 teams are now conducting long-term studies of Alpha Centauri, searching for slight wobbles in the light of each companion star that could indicate the presence of planets. If they find a planet that passes in front of one of the stars, astronomers will begin intensive studies to find out what it's like. One of their most promising tools will be the James Webb Space Telescope, scheduled for launch in 2014 or 2015. From a position 1 million miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. The largest space telescope ever built, it will offer an extraordinary new window into potential solar systems like Alpha Centauri. With its infrared light detectors, this telescope will be able to discern the chemical composition of a planet's atmosphere. And perhaps whether it harbors a moon, like Pandora. One prominent planet hunter predicted that if a habitable world is found at Alpha Centauri, the planning for a space mission would begin immediately. Here's that star duo seen by the Cassini spacecraft, just above the rings of Saturn. To actually get to this pair of stars, you'd have to travel as far as the orbit of Saturn, then go another 30,000 times further. Or put another way, if the distance to Alpha Centauri is the equivalent of New York to Chicago, then Saturn would be just 1 meter away. So far, the immense distances have not stopped us from launching missions into deep space. In 1977, the twin Voyager spacecraft were each sent on their way aboard Titan III Centaur rockets. After a series of gravitational assists from the giant outer planets, the spacecraft are now flying out of the solar system at about 40,000 miles per hour. They're moving so quickly that they could each whip around Earth in just 45 minutes. Twice as fast as the International Space Station. Voyager 1 has now traveled over 110 astronomical units. That's 110 times the average distance between Earth and Sun, or about 10 billion miles. But don't hold your breath. If it was headed in the right direction, it would need another 73,000 years to travel the 273,000 astronomical units to Alpha Centauri. When it comes to space travel, we've yet to realize the dream forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit, and eventually vast permanent space colonies. In time, he predicted, we'd evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem is that chemical rockets are just not efficient for long-distance space travel. To reach the speed needed to enter orbit around Earth, 17,500 miles per hour, the space shuttle must carry 15 times its weight in fuel. And that's efficient compared to some other rocket systems. And you'd need to be traveling more than 25,000 miles per hour to break free of Earth's orbit and go anywhere else. A NASA study showed that to send a space shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms of rocket propellant. Suffice to say, it's more mass than is in the entire visible universe. While only a very tiny percentage of NASA's budget goes to advanced propulsion, there are some promising ideas on the drawing board. Rockets powered by nuclear fuel, or plasma, a supervolatile gas. Huge sails pushed along by the pressure of photons from the sun. Ion drives. But to reach Alpha Centauri within a human timescale, we'll have to go with the most potent fuel in nature that we currently know. It's the science fiction fuel of choice, antimatter. In James Cameron's Avatar, hybrid nuclear fusion and antimatter engines power a mile-long interstellar spaceship. At a speed of 670 million miles per hour, this vehicle makes the journey to Alpha Centauri in just 6 years. Antimatter really does exist, as the mirror image of the universe we know. It consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Large amounts of antimatter were created and destroyed in the fiery dawn of our universe, the Big Bang. But somehow, in one of the great mysteries in science, we were left with a universe whose visible substance is almost all normal matter. The universe still produces antimatter through powerful collisions, such as a jet from a black hole slamming into a cloud of gas. When matter and antimatter obliterate one another, they emit gamma radiation that we can then detect with instruments such as the Fermi Gamma-Ray Space Telescope. Fortunately, black holes aren't the only way to generate antimatter. In giant labs, like the Large Hadron Collider, scientists accelerate atoms to nearly the speed of light and blast them together to expose their fundamental constituents. Small amounts of antimatter can be made this way, but it's incredibly expensive. With a dedicated facility, the cost of producing it might come down far enough to produce usable amounts. And that's the hope of one researcher. Dr. Gerald Smith has been working for over a decade to find a way to trap this volatile substance and store it in isolation from the rest of the universe. Smith and his colleagues have designed a trap the size of a cigar case. It sits within a tank filled with liquid nitrogen and liquid helium, designed to cool it down to 270 degrees below zero. Once injected into this trap, antimatter particles are suspended by magnetic fields within a vacuum as empty as deepest space. But the problem is that anti-electrons, called positrons, tend to repel each other explosively. That makes it tough to store more than a few at a time. This team now believes it may have discovered a pathway to storing large amounts over longer periods of time. Their solution lies in combining positrons with electrons, forming an element called positronium. In theory, with the right magnetic fields, these electrically neutral atoms might be held indefinitely. When released under controlled conditions, ultra-high energy antimatter beams could turn out to be ideal cancer killers, or lead to revolutionary industrial applications. Or perhaps, one day, they could power long-distance spaceflight. It wouldn't take much. Antimatter is so potent that it defies common sense. A chunk the size of a small coin could propel the space shuttle into orbit. Smith estimates that once in low Earth orbit, a human mission to Mars would take as little as 10 milligrams worth. The basic idea of an antimatter rocket is simple. A beam of positrons is released into the engine core, where it annihilates the surface of a metal plate. That creates an explosion that propels the craft forward. Another design uses a sail. A cloud of antimatter particles reacts explosively to its surface, propelling it forward. Short of traveling to another solar system, there may be good reasons to contemplate developing antimatter propulsion. A preliminary mission would speed beyond the orbit of Pluto, sending back close-up images of dark planet-like objects that ring the solar system out in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample particles that make up the interstellar medium, or send back unique data sets on dark matter, the invisible stuff that makes up the overwhelming portion of our universe. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to gradually accelerate to around 10% the speed of light That's 67 million miles per hour. It would then gradually decelerate as it approached its destination. At those speeds, hitting even a grain of dust could destroy the spacecraft, so it might be best to slow the journey down to a century or more. It's safe to assume for now that we would only send a probe to Alpha Centauri if we discovered a habitable world. There may be other choices in our solar neighborhood. They include Proxima Centauri, a red dwarf star 4.2 light-years away that may be gravitationally bound to Alpha Centauri. Beyond that, not quite 6 light-years away, is Barnard's star. Or there's Leland 21185, a red dwarf 8.3 light-years away. We already know it has 2 Jupiter-sized planets. There are at least 22 stars within 12 light-years of Earth. And any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peaks, to push ourselves past our perceived limits, seems to be a vital part of what makes us human. Yet, explorers of old set off not just because it was there. At times it was greed, hunger, fear, or despair that propelled them outward from their homelands and allowed them to endure their long journeys. Whether we attempt to make this leap to the stars may come to depend on how we regard this planet. To the physicist Stephen Hawking, the journey is imperative. "I don't think the human race," he said, "will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet." Indeed, we can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But today, we can see the often conflicting trends that could one day propel us out into the interstellar void. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing rate at which numbers of transistors can be placed inexpensively on computer microchips has become a metaphor for the advance of all technologies in this century. From a few thousand transistors on the first printed circuits of the 1970s, computer chips now have billions etched onto their surfaces. Even that number could seem amazingly small in another few decades. Many observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. On the other hand, major periods of scarcity may loom. In the 20th century, the world saw the largest increase in its human population, from less than 2 billion up to 6 billion. The world's population is now around 6.8 billion. It's expected to reach 9 to 10 billion by the year 2040, with the biggest gains in Asia and Africa. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. The scarcity of just simple clean water in some regions is already frightening. Now throw in environmental impacts, like rising sea levels, or the spread of deserts linked to a gradually warming climate. The culprit, to most scientists, is rising emission of greenhouse gases like carbon dioxide since the start of the Industrial Revolution. This map charts rising temperature readings from the year 1885 through to the present. In some places they've gone up by as much as 2.5 degrees Fahrenheit. Computer models project the trend out to the end of this century. Depending upon population growth, energy use, and conservation, temperatures could rise anywhere from 2 to 11 degrees more. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the impacts of war, natural catastrophes, or political upheavals? No doubt, if or when we launch our first mission beyond this solar system, the occasion will spur reflection on who and what we have become as a people, as a planet, just as the first missions to the moon and our neighboring planets once did. At first, we'll send a probe designed to relay basic information on what's there. On a world,
A subtle wobbling in the light of B. It could be a
It was hoped that lunar rocks would help solve that mystery. The Apollo 11 mission in 1969 marked the beginning of direct human exploration on the moon. During 6 missions, 382 kilograms of lunar rock were collected. Transporting all that from far-flung locations on the moon's surface required a lot of power. Apollo 15 finally developed the answer: the Lunar Roving Vehicle. Moving about freely on the moon's surface, this lunar rover could take astronauts farther afield than they could go on foot. However, developing the rover was very much a matter of trial and error. The lunar soil would be very different from Earth's. Engineers had to develop a vehicle that could operate on all kinds of terrain. Weighing just 200 kilograms, but capable of carrying a 500-kilogram load. A supercar that would be used to locate and transport rocks on the surface of the moon.
It was a great vehicle. They did a wonderful job in building it, you know, especially for those days. It's hard to believe now. We're talking how long ago? 40 years, 30 years? What are we talking, you know?
The last flight in the Apollo program was Apollo 17. On this mission, NASA finally included a scientist astronaut. This was a final chance to investigate on the moon's surface, a gamble that they could discover lunar materials of types never found before.
Hey, there is orange soil. Orange!
They succeeded far beyond their expectations, finding traces of the moon's dramatically violent past. This is the story of how the Apollo program developed a vehicle that could drive around on the moon, collecting rocks and soil that revealed billions of years of history. From time immemorial, people have cast longing glances at the moon. and wished for a chance to travel there. The first person to make that dream come true was the brilliant rocket scientist Wernher von Braun. He led the Apollo program, which actually landed men on the moon. A decade before the start of the Apollo program, von Braun's conceptualizations of space development were carried in a magazine. At a time when it wasn't even known if humans could traverse the distance to the moon and back, his blueprints for space development were bold and detailed. Each and every conceptual drawing overflowed with von Braun's enthusiasm for space travel. Exploration on the moon's surface was also included. A major role was to be played by lunar rovers. They were to function somewhat like the covered wagons that blazed trails through the American West. Clearly, even before space travel began in earnest, a lunar vehicle was conceived of as essential to exploration on the moon's surface. The latter half of the 1950s saw the start of a space race between the United States and the Soviet Union. These two superpowers staked their prestige on efforts to launch artificial satellites. In 1961, the Apollo program was launched, with von Braun playing a central role. The next year, development of a lunar vehicle began. Its construction proceeded in tandem with development of the Apollo rocket engines themselves. The best regarded prospect from that phase of development has been preserved. The MoLab, or Mobile Laboratory, built in 1964. The tires were huge. The vehicle was 9 meters long and weighed 3 tons. The inside was spacious. The design permitted 2 astronauts to live and work there for 2 weeks. The steering wheel and foot pedals were the same size as in an ordinary passenger vehicle. Development was spearheaded by 2 representatives of America's largest auto manufacturer, Chief Engineer Ferenc Pavliks and team leader Samuel Romano. Development went smoothly, but this rover never made it to the moon's surface. The problem was that massive body. NASA realized that they would need another rocket just for the rover, in addition to the one carrying the astronauts. In 1966, the year before the scheduled first trip to the moon, development on the lunar rover was suspended. It was a setback, but the developers waited for another chance.
Our job is laid out for us. Our task is laid out for us, yeah. But we didn't have any problems. We didn't think that we couldn't do it. It was our job to get it done, and we got it done.
In March 1969, faced with the upcoming launch of Apollo 11, the 2 men went to inspect the completed lunar module, or landing craft. They knew that their only hope of getting a rover onto the moon would be aboard the lunar module. But the lunar module had no space to spare, except for one unused compartment they spotted. It was a recess just 1.5 meters square and 0.9 meters deep.
Well, when we first saw this is impossible. We couldn't fit this larger vehicle in that space.
But Pavliks, the engineer, did not give up. He tried to see how compact he could make the rover. To carry 2 astronauts, it had to be at least 3 meters long. To get around on the moon's rock-strewn surface, it had to have large tires. But any way they calculated it, it was too big to fit on the lunar landing module. Was there no way to get it onto the lunar module? For 3 months, they experimented with mock-ups. Then, one day,
It's usually these ideas come very suddenly, you know. Eureka.
what was this sudden inspiration? Pavliks demonstrates with a 1/6 model.
Then the seats must be folded down. Then the front chassis, which is hinged, is folded over 180 degrees. Then the same way, the rear chassis is folded up. Then the wheels are folded in to the 45-degree angle. And then the complete assembly fits into that triangular shaped envelope, which is between 2 legs of the lunar landing module.
It was ingenious. A foldable vehicle was a huge step toward including a rover in the moon landing mission. Two weeks before the scheduled launch of Apollo 11, the 2 men took their model to NASA for a demonstration.
When we went to Huntsville, and the engineering people were very excited that hey, maybe this could work, okay? So one of the engineers said, why don't we show it to Dr. von Braun, who was the director of the Huntsville NASA organization.
Von Braun had the final say on lunar rover development. They had to arouse his interest and enthusiasm. Pavliks had an idea how to do that.
So he led the way to von Braun's office, opened the door, and I guided the vehicle into his office with radio control, that he couldn't see anybody but this little vehicle coming into his office. And he was on the telephone, saw this little thing coming in, and put the telephone down and said, what is this? And then we walked into the office, explained to him what the concept is, demonstrated all the folding up.
Von Braun listened intently. Then, suddenly,
he slammed his hand on the table and he said, we must do this. We must run a vehicle on the moon. And we convinced NASA to go ahead and do it, and we got a contract to do it.
the lunar rover concept championed by the 2 men had previously been scuttled. Now they'd been given a second chance. 2 weeks later, Apollo 11 was launched. The entire world awaited the moon landing with bated breath. The rehearsals for the Apollo program of putting men on the moon and bringing them back were over. This was the real thing. Three months later, the lunar rover project began in earnest. It had a new and powerful supporter, Saverio Morea. Morea was a capable manager who had overseen the successful development of the Apollo program's giant rocket engines.
All they do to send out the next model car, it takes them like 4 years before they're happy with the design and they can finally put one out on the street. That's different. We had to produce flight hardware for astronauts in a totally unknown environment in 17.5 months.
Starting with Apollo 11, NASA was planning on about one moon landing every 6 months. Apollo 15 was scheduled to undertake full-scale research on the moon's surface in 1971, just 2 years away. The lunar rover would have to be operational for that mission. The contract required development and production within a mere 18 months. This vehicle would be the first ever to run on a surface other than planet Earth's. It was a tough schedule, but they started development by trial and error. The first requirement was the capability to roam freely over the moon's rough terrain. The lunar rover would be useless unless it could easily surmount obstacles as high as 30 centimeters. The vehicle utilized technologies that were still unavailable to vehicles on Earth. It was an electric car whose 4 wheels were powered by dedicated motors drawing on 2 silver zinc batteries. The 4 motors put out a combined total of 1 horsepower. That was enough for the moon, whose gravity is only 1/6 that of Earth's. Operation was simplified. The manual controller had steering, acceleration, and braking functions all there at the driver's fingertips. Later, to accommodate the bulkiness of the astronaut spacesuits, the controller was reconfigured to a T-shape, so the driver's hand could rest on it comfortably. The design goal was operational ease. Maneuvering the rover was simple. Tilt the controller forward to start moving. Tilt right, it turns right. Tilt left, it turns left. Pull back to engage the brake. Push the button and pull back to put it in reverse. In test runs, actual astronauts checked out every feature very carefully. It functioned superbly. Everyone agreed development had gone well. Morea, however, spotted a surprising flaw.
Not so much the vehicle itself, but how the man would interact with a vehicle like ours in a 1/6G environment.
But what would it be like on the surface of the moon? No one could predict that. So they tested the rover's seats inside a large airplane, which was flown so as to simulate 1/6 of the Earth's gravity. This is the footage of that experiment. The astronaut flops about and can't get seated. There was no point in having a rover one could not ride. But this problem was solved with a little ingenuity. A 15-centimeter bolt protruding from the floor of the car body. The astronaut could then hook his foot briefly under the bolt, levering himself onto and into the seat. Problem solved.
That was the big one. Simple solution, but big issue. This was not simplistic. This was a spacecraft on wheels.
April 1970. By now, they had reached Apollo 13, but the lunar rover had run into a seemingly impassable developmental wall. The problem? The material and shape of those huge tires. In the vacuum of space, pneumatic rubber tires would blow out. They were simply not practical. What's more, on the moon, the terrain, scarred from the impact of countless small meteorites, is uneven, full of potholes. But in some places, the soil is finely granulated, like powder. The tires would have to do well on that sort of terrain as well. They needed something strong, resistant to temperature fluctuations. They thought of a material quite unsuitable for terrestrial tires: metal.
Should be flexible because it was carrying people, so the ride characteristic had to be such that it cannot be a rigid wheel. So we came up with this idea of making a flexible wheel, making it out of spring material.
So they created 10 types of metal wheels or tires and tested each and every type. It had to be lightweight and suited to any terrain. It also had to give a comfortable ride. This is the one they finally chose. Metal filaments were woven together at 4-millimeter intervals. This was a wire mesh tire.
This wheel is a very good simulation of an actual tire. It yields as you press on it, and it returns, and it has enough strength to carry the weight of the vehicle. So it seemed like it, and it can't blow out.
Romano's team had overcome their greatest obstacle. Where does a wire mesh tire get its strength and versatility? Kazuya Yoshida, who helped develop the Japanese asteroid explorer Hayabusa, ran some tests. He fabricated two 15-centimeter diameter wire mesh tires and attached them to a small testing unit. A rock was inserted in the test bed to create a 3-centimeter high obstacle. How will the tires perform? The test unit easily negotiates the obstacle. When tire meets rock, the tire changes shape to accommodate the rock. That suppleness in the wire mesh tire, allowing it to traverse both rocky ground and softer soil, is exactly what is needed on variable terrain like the Moon's. The rover was now outfitted with wire mesh tires. The next step was to simulate lunar conditions for full-scale testing. One trick was to have the rover lifted slightly by a crane as it ran, so it would be 1/6 of its real weight, as it would be on the Moon. Only after it passed numerous performance tests was the lunar rover deemed ready. Just 4 months before the scheduled flight of Apollo 15, the lunar rover was packed into the side of the landing module. And NASA was setting a new plan in motion. The Moon's surface has both dark-colored and light-colored areas. Up to Apollo 14, the Moon landings had all been on the dark areas. They are called seas, and they are flat. That made them relatively safe for landing. But the only kind of rock they could find in such places was basalt. There's plenty of that on Earth. So Apollo 15 would approach one of the light areas instead. The plan was to set the lunar module down near the edge of a dark sea, and then have astronauts set out in the rover for brighter, higher ground. NASA had not yet obtained any rocks from the Moon's highlands. July 26, 1971. With the lunar rover on board for the very first time, Apollo 15 took off for the Moon. Taking the rover made this an historic flight, one that marked the beginning of true lunar exploration. Four days later, the Falcon lunar landing module set down safely on one of the Moon's seas, near a mountain range. They were about to realize the fruits of 1.5 years of development. An astronaut held the rope that would release the lunar rover from its cargo bay. Back at Mission Control, the two men who had worked so hard to develop the rover held their breath. The rope is yanked hard, and the rover begins to emerge. All it took was one quick pull for the rover to start to deploy. In just 5 minutes, there was the lunar rover, ready to roll. But then came something unforeseen.
Okay. Got a deep hit. We're moving.
Extraordinary.
Negative. But I don't have any front steering, Joe.
There was no front steering at all.
Oops, yeah, it was oops. As a matter of fact, within minutes, I got a call from the vice president from Detroit, General Motors, that what's going on? Can you fix the problem? So it was a high, visibility type of operation.
No front steering could have been a serious setback. But the rover had a built-in feature that saved the day. The front and rear wheels actually operated in tandem in a four-wheel steering system. To turn right, for example, the front wheels would point right and the rear wheels would point left, all four contributing to the turn. On Apollo 15, the front wheels did not steer when first powered up, but the independently powered back wheels still operated sufficiently for the vehicle to be maneuvered. "40 minutes later, the rover was declared ready to explore the moon.
Ben, this is really a rock and rolling ride, isn't it? Never been on a ride like this before. Boy, oh boy. I'm glad they got this great suspension system on this thing. Boy.
Average speed, 12 kilometers per hour. The two astronauts riding the rover were just ecstatic. Then, suddenly, they realized they could no longer see the lunar module. Since the moon is only 1/4 the size of Earth, traveling 3 kilometers as they had put them beyond the horizon. But that was no cause for alarm. They had built-in technology that gave them distance and angle to the lunar module. The first ever lunar car navigation system. With no fear of getting lost, they were emboldened to go even beyond the sight lines to the lunar module. On the second day of exploration, they made a great discovery. It was while the rover was en route to higher ground. The two explorers were at the edge of a vast crater.
Okay, Jimmy, let's go to work. Roger. Look at that. Almost see twinning in there. Guess what we just found? I think we found what we came for. Crystal and rock, huh? Yes, sir. You better believe it.
It was a white rock, which they called the Genesis Rock. The highlands were composed of rock that formed shortly after the moon itself was born. Hitherto, the lunar seas had yielded only black basalt. What Apollo 15 retrieved from the highlands was a white rock called anorthosite. This discovery made it possible to construct a scenario explaining how the moon achieved its current shape and characteristics. 4.6 billion years ago, the solar system had only just taken shape. Right after the Earth itself was born, a body the size of Mars collided with it. This giant impact, as it's called, blew a vast cloud of debris out into space. The fragments were gravitationally attracted to each other and fused in a repeated process. The result was the Moon. As it took final shape, the Moon was covered in magma, molten rock heated by the energy from all those collisions. In time, as the Moon cooled, white anorthosite began to crystallize in the interior. With a relatively low specific gravity, the anorthosite gradually moved to the surface, where it formed the Moon's crust. So at one point, it is thought the Moon was entirely white. Then, however, the solar system was struck by a vast swarm of meteoroids. Impacts on the Moon created giant craters. They punctured the crust, through which magma pushed up from the Moon's core onto the surface. The magma, now lava, cooled in the form of black basalt. This is how the Moon's seas were formed. This account of the formation of the Moon is based on discoveries made possible by the lunar rover. In April 1972, Apollo 16 was launched. On this mission, too, the rover played a major role. It scampered easily over the Moon's rough terrain. And it covered a total of 27 kilometers, 10 times farther than an astronaut could have walked in the same time period. The lunar rover had proved to be indispensable to the Apollo program's moon-based exploration. Suddenly, it was the last Apollo mission. NASA hoped for a spectacular new discovery. The objective was a gorge, cut into steep mountains. This terrain was far more complicated than any attempted before. There was a good chance some strange new rocks would be discovered. And it was their last chance. So on Apollo 17, NASA sent in a ringer. For the first time, a scientist was aboard. A geologist named Harrison Schmitt. Nowadays, more astronauts than ever before have professional backgrounds in science and engineering. Their expertise is valued for conducting experiments in space. But on the Apollo program, given the extraordinarily complex operational requirements, all the astronauts except for Schmitt were military pilots. Schmitt had been fascinated by space since childhood, but he became a geologist. His chance to venture into space came when he was 29 years old.
It was on very short notice. The NASA and the National Academy of Sciences asked for volunteers for scientists to become astronauts in November of 1964. And I thought for about 10 seconds and decided that I would regret not volunteering, and so I volunteered.
Schmitt had never piloted anything more complex than an automobile, but NASA drummed new operational skills into him. Apollo 17 was the last chance to discover new moon rocks. Capitalizing on that chance was up to Schmidt. December 7, 1972. With one lunar rover and one scientist on board, this was Apollo's last chance. Schmidt was given the responsibility of piloting the lunar landing module. 4 days later, they had reached lunar orbit. The lunar module separated from the command module and began its descent to the surface. Carefully, they descended to a narrow gap between steep mountain ridges. In the end, Schmidt and his crewmates made a successful landing.
Stand by for touchdown. Stand by.
They had landed perfectly, in the middle of the valley. Surrounded by this magnificent scenery, the normally calm Schmidt could not conceal his excitement.
To all those who made it possible.
Really would be great to go to this valley, this deep mountain valley. It's deeper than the Grand Canyon of the Colorado. I mean, it was a very deep valley. It was splitting the ring of mountains around this large basin called Serenitatis. And it had these young volcanics. It had a lot of a very attractive thing.
Schmidt and another astronaut boarded the rover right away and set off to investigate. They traveled west to a point 3.5 kilometers from the lunar module. Right in front of them was a crater more than 100 meters in diameter. Schmidt's instincts as a geologist told him to focus his attention on this crater.
And I think everybody in Mission Control was excited about it too, because it was so unexpected.
The geologists in Mission Control could not conceal their enthusiasm either. Until then, there had been no indication that there had ever been volcanic activity on the moon. A close look at the sand reveals tiny globs of glass, 0.1 millimeters across. They called it orange glass.
It was a volcanic deposit, what we call a pyroclastic deposit. Certainly people in Japan are very familiar with volcanoes that erupt and throw glass and debris around. Well, this had happened on the moon.
The orange glass was created 3.6 billion years ago. At the bottom of a crater made by a meteorite impact, magma spewed forth from the moon's core. A fire fountain sprayed droplets of magma from 400 kilometers below the crust out into the cold of space, where they instantly cooled into globules of glass. Schmidt and his colleagues had discovered irrefutable evidence of volcanic activity on the moon. "36 years later, the Japanese unmanned lunar explorer Kaguya photographed the moon's surface with a special camera. It identified more than 40 locations on the moon where there was sand with the same composition as the orange glass. This confirmed that the Moon, like Earth, had seen a great deal of volcanic activity.
We were told later on that without the rover, NASA or the government would have cancelled the last 3 or at least 2 Apollo flights. So it was, in a sense, the rovers were saved the last 3 of the Apollo flights, because it was a new element in the exploration.
The riddle of the Moon's origin was solved by the Genesis rock and orange glass, and it was the lunar rover that led to these discoveries. It's been 40 years since the end of the Apollo program. But research is still being done on the rocks brought back from the Moon. New facts are even now coming to light. Alberto Saal is an associate professor of geological sciences at Brown University in the U.S. He's using Earth's latest technology to study the Moon's orange glass. When the magma spewed out of those lunar craters, it instantly formed glass globules that incorporated substances from the Moon's core. That makes them time capsules of the very origin of the Moon. Analysis yielded unanticipated results. Trapped in the orange glass were some of the same gases that exist on Earth, such as fluorine and chlorine. This supported the theory that the Moon came from the Earth. Another completely unanticipated substance was found: water. This was the first ever proof that there was water on the Moon. When Earth suffered the giant impact that gave birth to the Moon, the fragments of Earth dislodged into space were heated to 4,000 degrees Celsius. It had been thought that all the water would have evaporated. But where had the Moon's water come from? Currently, the world's only isotope microscope is being used to analyze the Moon rocks to solve that very riddle. Hisayoshi Yurimoto has been conducting research of this sort, including analysis of the Apollo mission's moon rocks. That includes measurements of deuterium, a hydrogen isotope. Amounts differ depending on the type of space object in which they are found. The water in the moon rocks contains from 0.02 to 0.03% deuterium. Comparable amounts of deuterium are found in another well-known type of space object: comets. In the solar system of 4 billion years ago, there were many more comets than there are now passing through. Yurimoto believes that the Moon was showered with a huge quantity of comet ice in that era, when the comets passed too close to the Sun. At that time, it recouped some of the water lost after the event of the giant impact. Since the Apollo missions, no one has walked on the Moon. But plans are underway now for new moonwalks. In 2009, the U.S. launched the Lunar Reconnaissance Orbiter, or LRO. It is parked in lunar orbit 21 kilometers above the Moon, from which it photographs the surface. This is an effort to compile detailed information for the next people who attempt to conduct investigations on the Moon's surface. This is one of the images captured by the LRO. It's the Apollo 17 lunar landing site. Those spidery lines mark where the lunar rover scudded across the Moon's surface. Their tracks remain even now. At the end of one of those tracks, a lunar roving vehicle, no longer roving. The rover was a major player in moon explorations of an earlier era. Now it sits there patiently, waiting to greet new explorers from Earth.